So, good day everyone. So, for today, we will be discussing Module 2, which is on acids, bases, and salts. So, here are our learning outcomes for this particular module, which are the following. So, at the end of this lesson or this module, you should be able to discuss the different theories involved in acids and bases, apply the concepts of chemical equilibrium to hydrogen ion concentration and pH, and then use dissociation and ionization constants in solving problems related to acid-base equilibria and titration. So this is very important for us to understand what is happening during our titration. How does a particular substance changes its color upon the addition of an exist substance? Or for example, an acid, if you will add now an indicator and you will add an excess volume of a base, it will change its color. It's because of the changes in its pH or the hydrogen ion concentration. So what are the significance of this particular module or the pH or acid and bases? So this serves as a factor to be considered in stability testing in specified medium. So for the basis of the preparation of isotonic solutions, so stability of certain solutions. So many chemical reactions proceed to completion at optimum pH. An important consideration in parenteral admixture to prevent now side effects resulting from incompatibilities or changes in the solutions due to pH. So compatibility of our solutions. So this particular module is divided into three parts. In first part would be is your different theories involved in your acids and bases or related to acids and bases. Next would be your dissociation constant or ionization constant, so which describes now an acid and a base. And lastly would be pH calculations, which is related now to the calculation of your acids, your bases, your salts, and your buffers. Right? So let's start with the first one, the first part, which is your different theories for acids and bases. So theories, we'll be discussing four different theories that are related to your acids and bases. So for us to better understand what are acids and bases, let's have a short review of our different theories. So first theory would be or was introduced by Soren Peder-Laurid Sorensen, or it is also known as your Sorensen's pH scale. So pH is the measure of the concentration of the hydrogen ion solution. So according to this particular theory, an acid and a base can be described according to a numerical value. So according to Sorensen's pH scale, so which is between 0 to 14, where 7 is neutral, and then values less than 7 are considered acids. And then values above 7 going to 14 are considered bases. Alright, so that is now your Sorensen's pH scales, which describe now an acid based on its numerical value that is usually less than 7 to 0. And then a base is a numerical value, which has a numerical value for above 7 to 40. Okay, so that's your acids and bases according to Sorensen's pH scale. Next theory would be introduced by Svante August Arrhenius. It is known as your Arrhenius theory of acids and bases. So acids generally, he describes acids as substances that liberates now hydrogen ions. So acids liberate hydrogen ions. So very good example of your acids would be your hydrochloric acid, for example, in an aqueous solution would now liberate a hydrogen ion and a chloride ion. So hydrochloric acid with water will now liberate hydrogen ion plus the chloride ion. So the same with your nitric, for example, nitric acid. So in an aqueous solution, it will liberate hydrogen plus a nitrate ion. Right? So that is your Arrhenius acid. So it liberates hydrogen. So it means if you're going to add an acid in water, it will increase now the hydrogen ion concentration, which will cause now a decrease in the pH, which will now give an acidic solution. Right? So that is your acid. Next, Arrhenius bases. According to Arrhenius theory, it is a base now liberates a hydroxyl ion. So it liberates a hydroxyl ion. So a good example would be your sodium hydroxide in water will now produce or will now ionize sodium ion plus a hydroxyl ion. So this one. So it liberates hydroxyl ion. So the same with your potassium hydroxide in water. So it will produce potassium ion plus a hydroxyl ion. So this is your Arrhenius base. So if, for example, you're going to add a base in water, it will now decrease the hydrogen concentration or hydrogen ion concentration, but it will increase now the hydroxyl ion concentration. So it will cause now an increase in the pH, which will now give a basic solution. So that is your Arrhenius theory. So next theory, other theories now will describe the limitation of other theories. So for example, the next theory, which is your Lewis theory, so Lewis acids and Lewis bases, which was introduced by Gilbert and Lewis. So this is one of the limitation of your Arrhenius, that not all acids will liberate now hydrogen and not all bases will actually liberate a hydroxyl ion. So according to this theory, an acid is actually an electron pair acceptor, and a base now is an electron pair donor. Right? So Lewis acid is considered an electron pair acceptor, and a Lewis base is an electron pair donor. So a very good example would be between your boron trifluoride, for example. So boron trifluoride and your ammonia. So which is your Lewis acid here and your Lewis base. So ammonia. It will now produce a compound which has a structure of this one. So which is your Lewis base and your Lewis acid. So here, your ammonia will actually donate its electron pair to boron. So it means your ammonia is the base and your boron trifluoride will accept now the electron pair coming from ammonia. So this will be your base and this will be your acid. So electron transfer between your base and your acid. So that is now your Lewis theory. Next theory, which is commonly accepted. So most of our solutions in this subject would be based on this theory. So this is again one of the limitation of your Arrhenius theory, that not all acid will actually liberate a hydrogen ion, and not all base will actually liberate a hydroxyl ion. So this was introduced by Johannes Nicholas Bronsted and Thomas Martin Lowry. Okay? So acids, they are considered now proton donors. So acids are considered proton donors. So proton donors in the form of hydrogen, and your bases are considered proton acceptors. So this is also explain the limitation of your Lewis. It's because for Lewis, he describes acids as electron pair acceptor and bases as uh, electron pair donors, which is also in the form of hydrogen. Okay? So an acid is an ionic or molecular substance capable of giving up protons, while base is an ionic or molecular substance capable of uniting with the proton. Or in simplified form, proton donors are acid, proton acceptors are your bases. So let's have a good example of this one. So for example, we have the hydrochloric acid a while ago. So plus water will actually produce now a hydronium ion plus a hydroxyl ion. So your hydrochloric acid as the acid, and your water here will serve as a base. So hydrogen will donate its hydrochloric acid will donate its hydrogen to water to form now hydronium ion plus a hydroxyl ion. The same with our example. So for example, we have ammonia plus water, which will now which is now your acid and your base here. It will produce now. So water is considered as your acid, and your ammonia will be considered as your base. So water will donate its electron to ammonia to form now ammonium and a hydroxyl ion. So which is now a proton donor and a proton acceptor. Alright, so that is your Bronsted-Lowry acid and Bronsted-Lowry base. So this particular theory also introduces now the conjugate acid-base pair. Alright, so what does this mean? So an acid, after donating its proton, will actually produce the conjugate base, and the base which will now accept the proton will produce the conjugate acid. So let's have the example again a while ago. So you have your HCl, for example. So HCl is the acid plus water will produce now a hydronium ion plus a chloride ion. Sorry, chloride ion. All right. So correction a while ago, this should be a chloride ion. So hydrochloric acid plus water will produce now a hydronium ion plus a chloride ion. So water will serve as a base. So water will donate its proton to water. So after donating now, the acid will produce the conjugate base. And then water, which is the base, will accept the proton from your acid to produce now the conjugate acid. So I repeat, conjugate acid is formed when a base now accepts a proton, and then a conjugate base is formed when an acid now donates a proton. Right? So hydrochloric acid plus water will produce now a hydronium ion plus a chloride ion. So the same with our ammonia a while ago. So ammonia plus water will produce ammonium and a hydroxyl ion. So water will donate its proton. So this water is considered as the acid, and then this is considered as the base. So water will donate its proton to ammonia. So after donating now, it will produce the conjugate base. And ammonia as a base will accept the proton to produce now the conjugate acid. Alright, so let's remember here, if the acid is strong, the conjugate base will be weak. So the same with your base, if it is strong, the conjugate acid is also a weak one. Right? Another very good example of this one, a common example would be between two water molecules. You have your two water molecules. So this is known as your protolysis or autoprotolysis. It's because uh, water is considered amphiprotic or amphoteric also. So when you say amphiprotic, it means it is capable of donating or accepting a proton. And then when you say amphoteric, it is considered as an acid or a base. This is called your autoprotolysis or protolysis, wherein there's an automatic transfer of proton from one water molecule. So let's say here, this is the acid water molecule, and then this is the base water molecule. So water, yung acidic water molecule will donate its proton to another water molecule, which is considered the base, to produce now the conjugate acid, which is your a conjugate acid, which is now your hydronium ion, and a conjugate acid, which is known as your hydroxyl ion. Right? So acid now will form or donate its proton, and then after donating, will form the conjugate. Uh, sorry, this is conjugate acid, and then this is the conjugate base. Right? So an acid, after donating its proton to a base, will now form the conjugate base, and then the base which accepts now the proton will produce the conjugate acid. Right? So that's one of the characteristic of your water. So let's have some characteristics of your acids and your bases. So acids generally are, or they have a characteristic sour taste, so this one. And then if you will test it with the litmus paper, it will change the color of the litmus paper from blue to red, or red to red, or no change. And then it reacts also with certain metals like your zinc to produce now a gas, which is your hydrogen. So it means it can liberate hydrogen when it reacts now with a certain metal, which is your zinc. And then if you're going to use an indicator, for example, phenolphthalein, so an acid solution is colorless or will produce a colorless solution. And if you're going to test it now with methyl orange, it will have a red color. And then base will have a bitter taste, this one. And then if you're going to test it with a litmus paper, it will change now the red litmus paper to blue, or blue to blue, or no change in the color of the blue litmus paper. And then if you will also uh, react it with a certain metal like your zinc and your aluminum, it will also liberate now hydrogen. And then acids, when it reacts now with the base, will form a salt, and then the same with your bases when it reacts with an acid will also form a salt. Okay? So those are now the different theories and some characteristics of your acids. So let's have some examples of your acids and your bases. So strong acids, what are a very good example of your strong acid? So common would be your halogens, halogen containing acid, like your hydrochloric acid. You have your hydrobromic. You have your hydroiodic. Only exemption here is the hydrofluoric, which is considered as a weak acid. And then you also have others like your nitric acid. You have your sulfuric. You also have your perchloric acid. So acids, they also have different characteristics. So they can be in the form of a monoprotic acid, a diprotic acid, and a triprotic acid. So monoprotic, you have your HCl. So it means it can liberate one hydrogen. A diprotic, a very good example, would be your sulfuric. So it has two hydrogen, and then phosphoric is a triprotic acid. So for phosphoric acid. And then weak acids, you have this one, hydrofluoric acid. And you also have the organic acids. So organic acids, like your carboxylic acid. Example would be your acetic, your formic acids. You also have the hydrogen cyanide or the HCN. So those are some examples of your weak acids. Strong bases, you have your group 1A and you have your sodium hydroxide. You also have potassium. You have your lithium. You have your rubidium. You have your calcium hydroxide for group 2. You have your barium. And you also have your strontium hydroxide. Sorry, 2. And then you, for weak acids, you have your ammonium hydroxide or ammonia. This is one of the most common weak acid. You have your zinc hydroxide. Also have your aluminum hydroxide. You have your ferrous hydroxide. And for organic compounds, you have the amines. So either primary, secondary, or tertiary amines. Okay? So the same with your acids, your bases can also be monoprotic, diprotic, and triprotic. Okay, so those are examples of your strong acids, weak acids, strong base, and your weak base.